Hi everyone, welcome back to chemistry. In this video, we're just going to look at intermolecular forces in action a little bit more deeply. So in our last lecture, we talked about intermolecular forces, or the different types that exist. The first one we said was London dispersion, and that all molecules and atoms exhibit that. Then we talked about dipole-dipole, and we said that only polar molecules will exhibit that. We talked also about hydrogen bonding, which we said was sort of a super dipole-dipole interaction, where if hydrogen was bonded to fluorine, oxygen, or nitrogen, then we have a very, very good dipole, and that's a particularly strong interaction, intermolecular interaction. And then we also said that the strongest of all of those is going to be the ion dipole, and that is between an ion and some polar molecules that could surround it. So those are the different types of interactions, but remember we also said that if you have lots of interactions, or the more interactions you have, I should say, the stronger those intermolecular forces are, and that has to do with a lot of behavior that we observe for different substances. So let's kind of look at that a little bit more closely. Specifically, I want to look at some three major, kind of areas that we see intermolecular forces being particularly important. So the first one is surface tension, and then we have viscosity, and then capillary action. What you can't see is this is, in my slides, is moving a bit, and it's showing the kind of like temporary nature of those interactions in yellow, the hydrogen bonds there. But let's kind of look closer at surface tension first. So surface tension, the kind of textbook definition is that it's the tendency of liquids to minimize their surface area to reduce potential energy. And what you can see here is that at the surface of this sample, which is water in this case, you'll see it says that we have a higher potential energy due to less IMFs, so fewer IMFs. And then in the next picture below that, we have low potential energy due to lots of IMFs. So let's kind of break this down, what this actually means. So if you think about water, right, and the surface of water, the water molecules that are at the surface, those have fewer neighboring interactions than those that are in the bulk or below, right? So this is, you could think of this as below the surface, and this is at the surface. So if you have fewer intermolecular interactions, because there's no extra layer up here of water molecules, if you have fewer of those interactions, that creates a higher energy state. So that's what this is talking about here. The reason for that is that you don't have a stable situation, all of these nice stabilizing intermolecular forces that are favorable to kind of stabilize your surface of the liquid. So because systems kind of want to minimize their potential energy naturally, what they'll try to do is the surface molecules will kind of be pulled inward, so pulled this way. And that allows the intermolecular forces to be a little bit stronger and minimizes energy. This means that the surface, because it's kind of pulled downward like that, pulled inward towards the rest of the solution, which we call the bulk, that leaves us with this kind of like skin type layer, which sounds a little bit funky, but it's kind of like this stretchy layer at the top, and we refer to that as surface tension. So what's important about surface tension and intermolecular forces is clearly they are related, but let's kind of summarize this. So surface tension is going to increase as intermolecular forces increase. Okay, so they are directly related. This is why, and there was actually a video in the slides, so if you have access to the slides on Canvas, you can watch that. But there's a video that shows that, or it's of an astronaut in zero gravity. And what he shows you is that water will naturally form these spherical drop in zero gravity. The reason for that is the sphere turns out to be kind of the smallest ratio of surface area to volume. So what this means is that all of these water molecules can kind of align themselves so that they're minimizing that surface area, maximizing intermolecular interactions with the rest of the solution inside the circle or sphere. And that allows it to kind of retain that spherical shape, which is really favorable. So that's why you'll see water forming those kind of droplets in zero gravity, or those spheres. Another example of surface tension that's kind of cool is if you've seen those stick bugs floating on water. The reason that they can walk on water is because of surface tension. So there's a really strong kind of surface tension-y layer at the top. And if you stick a little stick bug on there that's very light, not very heavy, it doesn't have enough weight to disturb the surface enough or break that surface tension. And so it will float on top of water. Whereas, more heavier bugs, or, us as humans, we would break the surface tension and, sink. So the question is, if you took that same stick bug and we know that it floats on water, or it can stand on water due to the surface tension of water. The question is, would that happen with propane, which is a different chemical substance? So if you look at propane here, it's got those 3 carbons, and that's why it's called propane, prop being 3. So if you look at propane, it's got just these alternating, it's just got a bunch of carbons in its chain. Sorry, not alternating. And then a bunch of hydrogens, right? So what do we know about the carbon-hydrogen bond? Is it polar or non-polar? Yeah, hopefully you answered that is a non-polar covalent bond. So the only intermolecular interaction or force that we would see propane exhibit would be what? Yeah, dispersion forces, right? So dispersion forces are weaker than something like a hydrogen bond, right? So hydrogen bonding is a stronger force. Therefore, we have that really high intermolecular force, which means our surface tension is really high as well. Over here, we have lower intermolecular forces, and so our surface tension is lower. So we would expect that our poor stick bug here would kind of sink into the propane. Okay, so that's surface tension, and basically we've already summarized it a little bit, but surface tension is going to increase as intermolecular forces increase. And the next thing I want to talk about is viscosity, and then we'll get into capillary action. So the question that I have is for you is, why do liquids have different viscosities? So if you look at this sample here, this is a picture of honey. And over here, this is a picture of good old H2O. So the question is, why is honey so kind of resistant to flow? Why is it so slow when you drop honey, versus, water pours very easily out. So why is that? Turns out, as you might have guessed, it does have to do with intermolecular forces. And specifically, it has to do with hydrogen bonds. So we know, you might be thinking, but Kayla, water has hydrogen bonds. That is true. Water does have hydrogen bonds. It also has London dispersion, dipole-dipole bonding, and we'll just reiterate that it has hydrogen bonding. Specifically, it has 2 opportunities for hydrogen bonding, right? Here and here. Now over here, we've got, look at all these. So first off, this is a really large molecule. We've also got lots and lots of opportunities for hydrogen bonding, right? In fact, let's count. That's 1, 2, 3, 4, 5, Oops, I just lost count. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 opportunities for hydrogen bonding. That's quite a bit, right? And we said that these are additive, right? So the more intermolecular forces something exhibits, the stronger those intermolecular forces are going to be overall, because you've got so many of them, and some of them are stronger than others. So all other things being equal, right? We have London dispersion, we have dipole-dipole, we have hydrogen bonding, but we have 8 of them, 8 opportunities for that. This is going to be a much stronger or higher number or a stronger amount of intermolecular forces. So higher intermolecular forces means higher viscosity or higher resistance. Oops, I meant to put an arrow there. Oh, that's almost like an arrow with a exclamation point. Sorry, let's do that. And then we can just put a fun exclamation point to the side. So higher viscosity, right? So that's the difference there between water and honey in terms of viscosity. So like we said, right, to kind of summarize and to kind of reiterate with some data, viscosity is going to increase as we increase the number of intermolecular forces or the strength, right? So in this case, this is a table and it says viscosity of several hydrocarbons at 20 degrees Celsius. What does the term hydrocarbon mean again? Yeah, you've got these hydrogen and carbon bonds, right? So hydrogens and carbons. So this is actually a scenario where we have, just a bunch of carbons bonded to hydrogens. And we don't really have any hydrogen bonding like up here, right? Remember, hydrogen has to be bonded to those very specific atoms. It has to be on the phone, as we say, F, O, or N. And it's not. And so there's no hydrogen bonding there. These are also not polar molecules because the bond, we said, between carbon and hydrogen is nonpolar. So really all of these only exhibit London dispersion forces. However, the longer the carbon chain, right? Pentane has 5 carbons. Hexane has 1, 2, 3, 4, 5, 6 carbons. Heptane has 7. Octane has 8. This is where those prefixes actually come in handy, so you don't have to count. Anyways, so the more carbons you get, right, the higher your molar mass, right, also means the higher your viscosity. So even though those are pretty low viscosities overall, right, because we don't have a ton of strong intermolecular forces, we do have lots and lots of London dispersion forces. And more London dispersion forces means greater IMFs overall, just because you have lots of them, right? Think of our gecko example. That's how geckos can climb walls. So the more you have, the greater the viscosity. The higher the resistance to flow, because you've got all of those interactions that are kind of holding your shape. Okay, so we also notice that there is some relationship between viscosity and temperature. So the question is, what happens to viscosity as you increase the temperature on a sample? So we can look at some data here, and I want you to just take a second to kind of analyze this. So hopefully you took a second to look at that. So this table says that it's the viscosity of liquid water at several temperatures. Over on the left, we've got temperatures ranging from 20 degrees Celsius to 100 degrees Celsius. And then we've got our viscosities on the right. And you can see as the temperature is increasing, the viscosity is decreasing. And that's something that we might be somewhat familiar with. If you do eat honey, you might notice that, yeah, when honey is pretty cold, it really has that strong resistance to flow. But as you heat honey up, it gets a lot easier to flow, or it has much less resistance to flowing. So what's going on there chemically? So as we increase the temperature, we are also increasing the kinetic energy. Remember, kinetic energy is the energy of what? Yeah, motion. So we're increasing the energy of motion. As we add in that heat energy, that kinetic energy is increasing. That means our atoms are moving really fast, colliding with each other every once in a while, but then immediately colliding with something else and going somewhere else, right? They're all kind of bopping around the container. So really high energy as you're increasing that temperature. That means at any given moment, the interaction between your two molecules in question, right, the intermolecular force between those two things, yeah, it could occur, but at the next second, that is no longer there because we've moved, our atom has moved, or our molecule has moved, and then there's suddenly an interaction somewhere else. And then that breaks, right? So these are very temporary because you've got so much kinetic energy. Compare that to when you're in a solid state, right? Right, lower temperature, solid state. Then you have lots and lots of opportunities for interactions that don't really, they just keep happening, right? Because you're all packed in together. Okay, so you increase the temperature, that increases the amount of kinetic energy, which decreases the intermolecular forces because they're very, temporary. Also, we know that one thing I should have mentioned is that, remember when we have like a gas, we have those molecules are pretty far from each other, right? And so even just from a distance perspective, if you have lots of kinetic energy, that means you have probably moved into the gaseous phase. And then just the sheer distance between those two molecules in question is going to be pretty far. So that's less interaction right there as well. Okay, so increasing the temperature increases the kinetic energy in your sample. And then intermolecular forces decrease, so that force of attraction is lower, and that lowers the viscosity overall because it doesn't have as much resistance to flow. It doesn't have to overcome as many forces of attraction in order to flow. All right, so let's summarize. That was quite a bit. So first, we talked about surface tension. We said that increases as intermolecular forces increase. And that can just be the number of intermolecular forces, or it can be the number and type, right? You can have stronger forces. And then viscosity, we said, kind of follows the same trend. It's going to increase as your IMFs increase and decrease as temperature increases. And then the very last topic that I wanted to go over for these intermolecular forces in action, like how do these kind of play, what role do these play in everyday life, is something called capillary action. So you might be familiar with capillary action, and you might not be. But if you've ever been to, the doctor and they take your blood, maybe they prick your finger and they use a capillary tube. Basically what a capillary tube is, it's usually made of glass, and it's this really thin glass tube. And what you'll notice is that after your finger is pricked, the blood will go up into the tube with no help from you. You just put the nurse practitioner or whoever's working on this with you, they just put the capillary tube on your finger and the blood will just move up the tube on its own. And this is actually due to intermolecular forces. Now, these are usually made of glass, but they can also be made of other things. It's just that glass is the most common because capillary action works the best on glass, and we'll talk about that. So if you zoom in on a sample of glass, what you'll see is that glass is actually made up of this structure here, or these different atoms. So we've got some silicon atoms bonded to some oxygens, and then you've got these sodium cations kind of hanging around. And when you look at some of these oxygens, you'll notice that there are negative charges, and those are, being, they're next to, right, or they're going to hang out with, I should say, your sodium cations. And so your sodium ions there are ions, right? So that those ions can interact with polar substances, namely the water that's in your blood, and you can get ion-dipole interactions. So let's make a note. That would be between, sorry, that's my abbreviation for between. Let me write it out. Between H2O that's in your blood and Na+, the ion, right? So it's an ion-dipole interaction. There are also these polar bonds. Well, maybe we'll make those yellow. And just remember that this is, you know, there's water coming in contact with these things. And then maybe we'll do purple for polar, or no, we'll say dipole interactions. And those are the silicon and oxygen bonds, right? Those are polar bonds. If you don't want to take my word for it, you can always look up some electronegativity numbers and kind of do some math and figure out the electronegativity difference and just double check. But they are, if you want to take my word for it, just trust me, they are polar bonds. So in that case, we've got dipole-dipole interactions, let's say between, I'll abbreviate it this time, between the H2O, between the silicon and oxygen and the water. So what am I saying here? So the point is, as that water is interacting with the glass, the water that's in your blood is interacting with the glass, it's going to be attracted to these different spots, and you're going to have these intermolecular forces. Now that's going to increase, right? Those intermolecular forces with the glass are going to increase, or I should say your water is going to experience those intermolecular forces with the glass. And that's going to cause it to ride further up the tube as they keep kind of, you know, all of those water molecules keep kind of being attracted to the glass. And that climbing is called capillary action. So that is the ability of a liquid to flow against gravity up a narrow tube. Now, it does need to be a narrow tube, and the reason for that is that if it's too large of a tube, then we don't have enough surface area between the hydrogen, or between the water molecules and the glass, so it's not as efficient of climbing. And then gravity will win and kind of keep it down. All right. We can also see capillary in action if we looked at like a meniscus. So this question says, you know, why do we see such a large meniscus when we mix hexane and water? We actually mixed hexane with water, or aqueous solutions, I should say, in one of our labs. And this is actually not as dramatic as I've seen. I've seen much more dramatic meniscuses. I don't know how to say it in the plural, but I've seen some pretty dramatic ones. So this is actually less dramatic than I usually see. But the reason that this is happening is that hexane, what do we know about hexane? So if we look at the structure of that, what type of intermolecular forces do we have there? Yeah, we really only have London dispersion forces there. And it's a non-polar molecule overall, right? We just have those carbon-hydrogen bonds. But with water, we have a polar molecule, which we've talked about many times. So if water is polar, and we know that glass has ion-dipole capability and dipole-dipole, or is capable of both dipole-dipole and ion-dipole bonding, in forces. If we know that, I lost myself there. If we know that water is polar and glass has some polarity to it as well, then water is going to be attracted to the sides of this container, this glass container, and it's going to start kind of climbing up the sides, right? As we're kind of increasing those interactions, those really stabilizing, favorable interactions. So water's like, oh, I want to go up this glass here. Now, if hexane is nonpolar and the glass is polar, hexane's going to want to get as far away from the glass as possible. So you get this kind of dipping in the middle here, where hexane is like, I just want to be in the center. I really would prefer to be away from that glass. Because hexane's like, well, at least with water, it's just a polar molecule. There's no ions in there. With the glass, there's a bunch of sodium ions that I really don't like, because they definitely have that strong charge. So it will kind of form this meniscus that way, and it looks pretty cool. All right, so in summary, and this is the last the last slide that we'll do today. So in summary, we looked at viscosity and surface tension, and the last one that we checked out was capillary action. And again, you guessed it, capillary action is going to increase as the IMFs increase. Okay, just like we saw with surface tension and with viscosity. So these IMFs are really, really important, and they govern a lot of behavior at the macro scale. All right, that's it for today. I will see you tomorrow for